Welcome. Elliptic curves are one of the most important objects in all of mathematics, and they are cubic curves. And if you first start to research the topic of elliptic curves online, one of the things that you learn about them is this kind of strange cubic equation. And you might start wondering, what is this about the cubic that makes it so special? Why not other degree polynomials? The mathematicians, as you try to sort of look up elliptic curves, seem to be obsessed with just studying cubic curves rather than, say, quartic curves or curves that are given by quadratic equations or anything else. So there are several reasons for this, and one of the reasons we're going to be talking about today. And that has to do with a very special property of cubic equations. In particular, we want to see what happens when you intersect a cubic curve with a line. So, more precisely, if I draw a cubic curve, the kind that I'm interested in, it will have this sort of shape. What I drew here is an example of an elliptic curve. The elliptic curves are not ellipses, they are certain cubic curves, as you will see in the course of this class. But the thing that I'm interested in right now is if I intersect this curve with a line, well, it looks like from my picture that it would intersect the curve in 3 points. But just because I drew this picture and it looks in a certain way doesn't necessarily mean that that's how these curves and how lines intersecting them always behave. So let's study cubic equations from the point of view on how many times a line can actually intersect them. So to do this, I want to first start with a general cubic polynomial. So I'm going to take a function f of x, which will be a cubic polynomial. So I'm going to write ax cubed plus bx squared plus cx plus d for the equation of that cubic polynomial. And I should tell you where these coefficients live. So for me, the coefficients will be real numbers. So, examples. You are very familiar with cubic polynomials, well. 3x cubed plus pi plus 1x squared plus ex plus 7/2 is a polynomial that is a cubic polynomial, and all its coefficients are real numbers. So in particular, I sort of specifically put in there a pi, so pi plus 1 is a real number, and e is the Euler's constant, also a real number. 7/2 is a rational, so also a real number, and integer 3 is also a real number. Right? I mean, but some of them, of course, could be 0, so x cubed plus 7x is a cubic polynomial. So I would not call this cubic if the coefficient in front of x cubed were 0. So the name comes from the fact that the coefficient at the cubic power is actually non-zero. So I would say, so f is called a cubic polynomial if a is not 0. If a were 0 and b wasn't 0, then we'll call it quadratic. If a and b were 0 but c wasn't 0, we'll call it linear, and otherwise, if all a, b, and c were 0, we would call it just a constant. But we're interested in cubic polynomials, so this doesn't have to, of course, always be 3, right? I don't want to have you that wrong impression. So 2/5 is another possibility for a coefficient here. So I want to study the roots of this polynomial. So just to remind you, so alpha, a complex number, so C will stand for complex numbers, is called a root. A root, or a complex root, of f if f of alpha is 0. And so how many complex roots can a cubic polynomial have? You know that's at most 3. There's a fact from algebra, and in fact there is a difficult theorem called the fundamental theorem of algebra that tells you that every cubic polynomial with complex coefficients, so we're looking here at a polynomial with real coefficients, but remember real numbers are also complex numbers. That's important to remember. So if I take a cubic polynomial with real coefficients, that is also a cubic polynomial with complex coefficients. And every cubic polynomial with complex coefficients has 3 complex roots counted with multiplicity. So let's discuss this, what that actually means is counted with multiplicity. So let's first write down the statement here. So the fundamental theorem, this is called the fundamental theorem of algebra. This is not an easy result. It was what Gauss got his PhD for, proving this theorem. So every polynomial of degree n greater than 0 with complex coefficients has a root, has a complex root. More precisely, it has exactly n roots. If you count multiplicity. Well, what's the degree of a polynomial? That is this power here that has the largest power of x in the polynomial that has a non-zero coefficient in front of it. So degree of a cubic polynomial is 3. So exactly n complex roots, so a cubic would have exactly 3 complex roots when you count it with multiplicity. That a polynomial has at most, of degree n, has at most n roots, that's actually a consequence of some fact in abstract algebra that says that the ring of polynomials with coefficients in a field has the property of unique factorization. So there's only sort of one way to write it as x minus a root times x minus another root, and so on, maybe up to permutations of these factors. But we're not going to get into this. We don't really care for the proof of that. We'll take this fundamental theorem of algebra, knowing that every cubic polynomial has now exactly 3 roots counting multiplicity. We will not be so interested in complex roots, actually. We'll be interested in real roots, and then later in rational roots. But this is sort of our starting point here. So what does that mean, this multiplicity? So And I'm just going to discuss this on the example of cubic polynomials. So what does it mean that a cubic polynomial with complex coefficients has exactly three complex roots. Counting multiplicity. So what does it mean? So it means this: if I take that cubic polynomial of mine, so f of x was ax cubed plus bx squared plus cx plus d. Remember, a was not 0. And the a, b, c, and d, for now I'll just take them to live inside the complex numbers, but we will be interested in a more special situation when they actually are real or even rational. So this theorem then tells me then there exist complex numbers alpha, beta, gamma, not necessarily distinct, not necessarily distinct. So some of them can be the same root, such that my polynomial f of x can be written as a x minus alpha, x minus beta, and x minus gamma. Okay? In a moment I'll explain to you what it means to have then, for a root to have certain multiplicity.